Welcome all to today's lecture. Myself Assistant Professor Tukur Gupta from Ajay Kumar Garg Engineering College, Ghaziabad. The subject that I am covering in my lecture series is Embedded System. Code is KOE 062. Today I am going to discuss the programming models which are used in Embedded Product Development Life Cycle, that is EDLC. Today I will cover data flow graph, state machine model and sequential program model. When we talk about the computational models used in embedded system design, so these are the 5 important programming models, that is data flow graph, in short we call it as DFG, state machine model, concurrent process model, sequential program model and object oriented model. First, with the very first and very common and simple model is data flow graph, that is DFG model. It translates the data processing requirements into a data flow graph. So, whatever are the processes that will be followed during the product development in the embedded application, all those data processing requirements are presented in the form of a flow graph. So, this is a data driven model. Basically, the data is the main driving force in this model, in which the program execution is determined by data. So, this model emphasizes on the data and operations on the data. So, this is the main focus in this model, which transforms the input data to output data. So, this is a visual model, we can say. I will show you the example in the next slide. This is the visual model in which the operation on the data or the process is represented using a block, that is a circle, and the data flow is represented using arrows. So, the process in this model is represented using the block, or we can say in some models it is represented using the circle, and the flow of the data from one process to another, it is represented using the arrows. An inward arrow, so arrow can be of two types, inward and outward arrows. So, inward arrows to the process represents the inputs, and outward arrows from the process, that is the circle we are talking about, it represents the output data in this DFG notation. So, embedded applications which are computation intensive, we can say, or they are data driven, these are modeled using this model. So, DSP applications are typical examples of this, because in DSP applications the main focus is on the various process nodes and the data flow between those nodes. So, the DSP applications is a very perfect example for the data flow graph. So, in this model a data path is the data flow path from input to output. It is said to be acyclic if it does not contain multiple values for the input variable and multiple output values for a given set of inputs. Let us see what it is saying. Suppose let us have a look at the implementation of the DFG. So, in those applications where the easy mathematical computations are required, so DFG is the best choice for the model to be used in that application. So, here suppose one of the functions in our application contains computational requirement like this. So, x is equal to the addition of a plus b and y is equal to the subtraction of c from x, that is x minus c. So, we can see the output of one function is used as one of the operands in another process. So, let us see what is happening here. So, this is the process node, it is representing a process which is the process of adding the two numbers. So, a and b, these are the two operands which are being added in this process. The output of this process is represented by x, and here the output from the first process is being used as the input for the another process. This is another process which is the subtraction of one operand from the other. Here the second operand for this new process is c. So, here y, that is the output of the next process, it is represented by the x minus c. So, in this way this is the acyclic graph, because here all the process flow, or we can say all the data flow takes place in the single direction. There is no sort of feedback. The output of one process is not going as a feedback to the another process. So, in this way, this is the perfect example of a cyclic data flow graph. So, this is what he is talking about, that the data flow graph model is said to be acyclic if it does not contain multiple values for the input variables and multiple output values for a given set of inputs. So, the feedback inputs, events, etc., are the examples for non-acyclic inputs. So, the graphs where there are the feedbacks present in the process, those are known as the cyclic graphs, or we can say non-acyclic. A DFG model translates the program as a single sequential process execution. So, it is a simple modeling of a process in which certain inputs are there and they are being fed to the process and they are being executed and giving some output related to that particular process. So, in this way it is a so it translates a sequential flow of program into a process execution, that is a model. Now, let us so we have already understood this application, this example. Another variant of this DFG graph is control data flow graph, that is it uses a data flow graph as an element, adding constructs to describe the control. So, where in those applications where are the many controlling applications are also present in the system, then that application is modeled using the control data flow graph. So, in that model there are some conditions which are evaluated in between the various processes, and depending upon the fulfillment of those conditions, the next process occurs. We will have a look at the example. So, in this control data flow graph we have two types of nodes, that is one is the decision node and another is the data flow nodes. So, similar to the ones shown in the data flow graph. So, data flow nodes are very common, like there was the circle like in this example. So, these nodes are known as the data flow nodes, these circular nodes. And another one are the decision nodes, which are commonly generally used generally represented using this rhombus. So, in this some condition is put, and depending upon the fulfillment of the condition, then only the data flows accordingly. So, the data flow node encapsulates a complete data flow graph to represent a basic block, and we can use one type of decision node to describe all the types of control in the sequential program. So, there may be a rhombus represented using rhombus, or some other figure can be used. The steps may have loops or condition statements in between. So, there can be a loops, because when there are the conditions put in between the processes, so obviously they will lead to some feedback loops and some feedback to the previous process, and in this way there may be the existence of loops and or condition statements in between the processes. The data that is input generate the data output after a control data flow as per controlling conditions. Outputs and path taken after the steps depends on the control statements for various decisions in a process. So, the outputs or the root of the data, it is decided depending upon the fulfillment of the conditions. So, in this model a diagram graphically represents the conditions and the program flow along a condition dependent path. So, the program flow depends upon the condition that is being presented in between the various processes. So, this diagram also represents the effect of events among the processes and shows which processes are activated on each specific event. So, by event we mean the triggering inputs. So, it depends upon the inputs that whether the condition will be fulfilled or not, and depending upon that the data flow direction is decided. So, this is an example of control data flow graph. Here the condition is placed inside a rhombus. Condition can be true or condition can be false. So, there are two two states of the condition. So, if the condition is true, the data flow goes to this side. So, there is another process, this is another process, and so the fulfillment of the condition leads to this path and the non-fulfillment of the condition leads to this path. So, it goes to another process in case of the condition is false. Now, next is another process placed here, and the ultimately in the this figure is showing that whether the condition is false or true, ultimately both the paths go to this process. Yes, from here only, here also and from here also, both the paths are going to the same process. Now, again there is another test condition. So, there can be the multiple outputs of this test condition. So, depending upon the outputs of this test condition, the different processes are executed. So, if the condition 1 is fulfilled, then this process occurs. If condition 2nd is fulfilled, then this process occurs, and if condition 3 is fulfilled, then this process takes place. In this way, the data flow goes on in this control data flow graph. So, here the circle represents each process called node in the control data flow graph. A directed arrow towards the circle represents the data input or the set of inputs, we can say. So, this arrow represents some input is going on in this process. A directed arrow from the circle represents a data output, that is, there may be a circle or there may be a rectangle, it depends upon the implementation. So, it represents certain output. So, the data, so the arrow coming out of certain block. So, this is the block and the arrow coming out of this block represents the output out of that box. A box that is a square or rectangle with its diagonal axis horizontal and vertical may represent a condition. So, there can be a square or there can be a rhombus represented by this rhombus, and this shows some condition is being represented in the system. So, what are the advantages of this control data flow graph? That it helps in understanding all the conditions and in determining the number of paths a program may take. It guides us how software to be tested for each path starting from the decision node. So, this is a very useful graph in case where in those applications where the conditions have to be tested at one or the other point of time. So, in those applications this control data flow graph is very useful. It again it helps in analyzing the program in terms of complexity. So, time to time we can analyze the complexity of the system depending upon the test conditions. So, it is useful in that case also. Now, after data flow graphs and control data flow graph, we come to the state machine model. So, this model is used for modeling reactive or event driven embedded systems. So, these models are used, this model, the state machine model is used where the lot many conditions have to be analyzed time to time. So, basically this model is not data driven, but is event driven. So, if there are multiple numbers of events present in certain application, then we have to use this model for our application. So, the processing of those events and the behavior are dependent on the state transitions. So, they are used in the control and industrial applications. These are the typical examples of this state machine model application. Before going into details of a state machine model, let us understand the basic terms used in this model, that is the states, events, actions and transitions. So, what is a state? The current situation of a process is known as the state. So, whether there can be a waiting state, there can be a blocked state, there can be a running state like this. So, state is that the representation of a current situation is a state. Event is an input to the state that triggers that state the event act as the stimuli for that state transition. So, event is always an input which acts as the stimuli which triggers that process, and it triggers the process to react, and it leads to the transition from one state to another. For example, maybe certain process is in the blocked state, and after the receiving the input, after receiving the trigger input, it may change its state from blocked to ready state, or the one which is in the ready state maybe it gets its state gets changed from ready to the running state. So, in this way some events act as the stimuli to change the state from one to another. So, the transition is the movement from one state to another is transition. Action is an activity to be performed by the state machine. So, action occurs when the transition occurs when certain stimuli acts as an input to the state. So, in this way these terms are interrelated to each other. So, the finite state machine, that is the FSM model, is the model of discrete behavior which consists of a finite number of states, transitions between those states and actions. So, what we understand by the term finite state machines? First of all, state machines that represent certain states. Now, the finite state machines means the applications where there are uncountable states, then we cannot model it in some design. Okay. So, but these finite state machine models, the specialty is this, that we know what are the finite stages, and that is why we can model it. So, this is how we are able to model it. So, we know that in certain applications, suppose there are 3 states, we know that the amount of the states, the number of states are well defined, we know the number of states. So, that is why these are known as the finite state machine models. So, we know that there are 3 states, state 1, state 2, and so like suppose this is state 4, state 3. So, now the transition from one state to another is occurring here, another transition 2, transition 3 and transition 4. Like this one state changes from to another state, that process is known as the transition, and the input stimuli which should be there which changes that state to another one. So, here I am discussing a seat belt warning system. So, as an example I am discussing it. So, what is this seat belt warning system? So, first of all I have to recognize the number of states present in this system. When the vehicle ignition is turned on and the seat belt is not fastened within 10 seconds, suppose I have switch on my vehicle. So, vehicle ignition is turned on and I have not fastened my seat belt within 10 seconds of ignition on, the system should generate the signal, that is the alarm signal, for 5 seconds. So, the first condition is this, that within 10 seconds of switching on the ignition of the vehicle, the alarm signal should switch on for 5 seconds. The alarm is turned off when the alarm time expires, that is the 5 seconds of alarm time. This is the 5 seconds time is for alarm. So, if either this 5 seconds have passed, so alarm time is off, expired, or if the driver has fastened the seat belt, then also the alarm should be off. So, whichever happens first. So, this is the condition. Let us understand this, how it can be modeled using state machine model. So, here we first of all we have to recognize the states. So, first state is alarm is off. So, this is state 1. Now, another is that it is waiting. So, waiting for what? Waiting for the condition that it should be on or off. So, waiting, and alarm on is another state. The events are ignition key on. So, events are the trigger inputs, stimuli. So, if the ignition key is on, if the ignition key is off, timer, if the timer has expired or not, if the alarm time, that is of 5 seconds, this alarm timer was of 10 seconds, alarm time was 5 seconds. So, it has been expired or not, and the seat belt is on. So, these are the events, and the states are alarm is off, alarm is on, or alarm is waiting for the stimuli. So, using the finite state machine, this can be modeled as like this. So, this is the alarm off, alarm is off here. So, this is alarm off. Now, the vehicle is switched on, that is the ignition key is switched on. It is now the system is waiting for what? Waiting for 10 seconds, because after 10 seconds, if the belt is not fastened or the ignition is not being put off, then the alarm will occur. So, it is waiting for those 10 seconds. After the 10 seconds, if the ignition key is off, so this is the one of the stimuli. If the ignition key is on, the state waiting will be transitioned to alarm off. So, again it will go to the state of alarm off if the ignition is off, if the seat belt is on. So, if the person has fastened the seat belt or if the ignition keys has been put off, then this state of waiting will again go back to alarm off state. But if after the waiting state the timer has expired, then alarm will be off. So, this is waiting state, this is alarm on. So, alarm on. So, if the timer will expire, that is the 10 seconds of waiting time is expired, then alarm will be on. So, in this state the alarm will be on here, and if now when it will go back to alarm off state, if after the alarm is on, if the seat belt is fastened or the ignition key is off, then again it will go back to alarm off condition. Or if the alarm time has been expired, alarm time is of 5 seconds. So, if it has been expired, then again it will go back to alarm off state. So, in this way we are able to recognize the states and we are able to recognize the stimuli for each of these states. So, this is what I have already told you. Now, let us see another example, that we are designing an automatic tea or coffee vending machine, which will give the tea or coffee based on the insertion of the coin in the machine. So, the tea or coffee vending machine is initiated by user inserting a 5 rupee coin. After inserting the coin, the user can either select coffee or tea or press cancel to cancel the order and take back the coin. So, we have to again recognize the states. So, the various states are, there are 4 states that wait for the coin. After the insertion of the coin, the machine will wait for the user input, whether he or she wants the tea or coffee. Another state will be it will dispense the tea, another one will be it will dispense the coffee. So, there are 4 states. State A is wait for the coin, state B is wait for user input, state C is dispense the tea, and state D is dispense coffee. So, again we will look at those the transitions between those states. So, the system is at the state 1 first of all, that it is waiting for the coin. If the coin has been inserted, this is coin inserted, then it will go to state B, that it will wait for the user input. If the T button is pressed, it will go to state C. If the coffee button is pressed, it will go to state D. So, state C is dispense tea, state D is dispense coffee. But here when it was a state A and it went back, went to the state B, that is the coin has been inserted, then if the request has been cancelled, it is possible that this is one of the event that the request has been cancelled, then it will again go back to the previous state, that is the wait for the coin. So, in this way after the dispensing the tea, it will go back to the state A, that is the waiting state, or after dispensing the coffee, it will again go back to the waiting state. So, in this way we have recognized that there are 4 states of this application. So, today we discussed about the 3 models, about the 2 models basically, that is the data flow graph and the finite state machine model, and we studied one more variant of data flow graph, that is the control data flow graph. So, by now you must have understood that depending upon the application, embedded application, we have to understand that which model we have to select. If the application is data driven, then we have to select the data flow model. But if our application is the event driven and we have to analyze the lot many conditions, lot many events, then we have to use the this finite state machine model. So, in this way we can make choice between the different models available. That is all for the day. In next lecture we will study about the further models used in the EDLC. Thank you.